kind introduction, and thanks everybody for showing up in this maybe early morning in the East Coast. Then today I'm going to talk about the problem of ethics and welfare in the design of randomized experiments. So the motivation is very simple. That is needless to explain to this crowd, but now it's the sort of the golden age of RCT or A/B tests, right? That RCT is a social standard of evidence, not just in economics, but also in the whole society, I would say. Then if we look at the real-world implementation of these RCTs, then we are going to immediately notice a couple of very striking features. First of all, these RCTs involve a really big number of individuals as experimental subjects. So I'm going to be specific about a couple of numbers, but looks like hundreds of millions of individuals participate into some RCTs in recent years. Then for such a large population of experimental subjects, many of these RCTs randomize very high-stakes experimental treatments. Say, think about some medical clinical trial where the treatment is a cancer drug or a new HIV prevention drug. These things are literally life-threatening. And now so we are seeing an inflow of lots of RCTs about COVID-19 vaccines as well. Then even in social and economic domains, many RCTs allocate critical treatments such as basic income and health insurance, police patrol, and so on and so on. Then these 2 points jointly mean that what's happening in RCTs influences the lives of numerous individuals. So given this high-stakes nature, what I'm going to try to do today is to provide a design of a randomized experiment, and that can improve the welfare of participating experimental subjects while producing enough experimental information to do causal inference and impact evaluation. More specifically, I'm going to use a microeconomic model or a mechanism design framework to derive a Pareto optimal stratified experiment, so to speak, with the following 3 features. So first of all, my proposed design has a welfare optimality property in the sense that it creates a Pareto efficient allocation of treatment assignment probabilities, where the experimenter assigns each treatment to subjects predicted to experience better treatment effects or to subjects with stronger preferences for that treatment. For the second preference aspect of subject welfare, the proposed design has also incentive compatibility. That is, it provides subjects with simple incentives to tell the truth about what kind of treatments they really want. Finally, since this is an experimental design, it also should allow the experimenter to estimate or unbiasedly estimate the key causal effects that are usually estimated with data from an RCT. And the proposed design indeed has such a good information property. So I'm going to propose an experimental design with the 3 features, welfare, incentive, and information. Then after developing such an experimental design as a purely theoretical concept, I'm going to also verify and quantify these properties through some empirical illustration. And my empirical analysis is going to be based on data coming from a water cleaning experiment done in Kenya in mid-2000. And through this empirical application, I'm going to find that the proposed design is indeed substantially better than RCTs in terms of these 3 properties. Specifically, it's possible to improve the predicted welfare of experimental subjects while producing almost the same treatment effect estimates with almost the same standard errors or precision. So this project is a mix of some methodological development and an empirical illustration. And it's clearly mission impossible to explain all of these points in 25 minutes. So I'm going to mainly focus on the sort of the conceptual side of this experimental design and provide only a brief summary of the empirical result. Then before jumping into the analysis, let me spend just 1 minute into explaining, why this problem is important and interesting. That is, why should we care about subject welfare? So my answer to this question consists of 2 simple facts. So fact number 1, RCTs enroll hundreds of millions of individuals as experimental subjects. So to be precise, I computed the number of patients who participated into some medical clinical trials from 2007 to 2017 based on WHO's clinical trial registry. Then this analysis or exercise shows that, okay, the total number of clinical trial participants was over 360 million during this decade, okay, which is even larger than the entire US population. And I did the same computation for social and economic RCTs as well, based on the AEA's registry. Then the number turns out to be order of magnitude smaller, but still more than 22 million individuals and households participated into economic experiments. So it's probably fair to say that hundreds of millions of individuals and maybe billions of individuals if we include online A/B tests conducted by web companies and tech companies. Okay, this sort of massive number of individuals are participating in the RCT in recent years. Then for that sort of subject population, many of these RCTs create very high stakes resource allocations. And this high stakes nature is kind of obvious in the case of many medical clinical trials, right? That is, think about COVID-19 vaccine trials or this specific clinical trial where the treatment was a newly developed cholesterol lowering drug. And this drug was randomly assigned to over 4,000 heart disease patients. Then this drug turned out to be a miracle drug, so that the treatment effect on the 5-year mortality rate was more than 30% reduction compared to the baseline level. So then from this single clinical trial alone, the lives and deaths of hundreds of individuals depends on how to design this clinical trial and who gets which treatment. Then this motivates me to think about the problem of welfare, okay, in the design of RCTs. Then I'm going to use the following stylized framework where we have a bunch of experimental subjects, I1 to IN, to be assigned to a bunch of experimental treatments from T0 to Tn. Okay. Then I assume that the experimenter has a couple of measurements about subjects' predicted welfare. A key measurement about subject welfare is probably some information about how effective each treatment is likely to be for different types of experimental subjects. And I'm going to use this ETI symbol to denote this predicted effect of each treatment T on each subject I. And these predicted effects are supposed to be coming from prior experiments or observational studies, as is sort of always done in medical and business domains. Then even conditional on these predicted effects as a first welfare measure, there is ample evidence that different subjects have different preferences, okay, about what kind of treatments they want. And to capture this preference aspect of subject welfare, I'm going to use this WIT to denote each subject I's willingness to pay, or WTP, for each treatment T. So W and E are going to be my sort of prior welfare measures. And I'm going to use this first treatment T0 to denote a control or placebo, okay, to be compared to other things. And let's normalize both E and W, okay, so that both E and W are 0 for this control. Okay, so everything is going to be measured relative to this control thing. Okay, so then that's the framework. And any question or clarification? Good. Then, given this, different experimental designs produce different treatment assignment probabilities. Okay? The benchmark experimental design is the usual RCT, okay, which assigns each subject to each treatment, okay, with some constant assignment probability denoted by this P super RCT, okay. And I'm going to denote this PRCT as the ratio of each treatment T's pseudo or quasi-capacity CT relative to the total number of experimental subjects, N. Okay. Now, from this expression alone, it should be clear that this RCT doesn't directly incorporate any information about willingness to pay W and the predicted effects E. So my first theoretical question is how to sort of incorporate this additional rich data about subject welfare, especially willingness to pay and predicted effects. And to answer this question, I'm going to develop and consider the following experimental design, which I'm going to call experiment as market, or in short, exam. So this exam is an application of microeconomics or market and mechanism design to this experimental design program. So at a high level, let's create a completely hypothetical centralized market economy in the experimental's computer. And in this market economy, commodities or goods to be allocated correspond to treatment assignment probabilities. And consumers correspond to experimental subjects. Then let's substitute the experimental's data into this economy to compute the resulting competitive market equilibrium allocation of treatment assignment probabilities. So my proposal is to use this competitive market equilibrium as a possible experimental design. More specifically, let's find any personalized price competitive market equilibrium, which is defined as a combination of feasible treatment assignment probabilities P star, as well as their prices pi with a few equilibrium restriction. So the formal definition is slightly complicated. So let me go through these pieces one by one. So first of all, this pi TE object, this red object, okay, is the price of 1 unit of assignment probability at treatment T, okay, for experimental subjects for whom the predicted effect of this treatment T is given by E. Here, so E is just some number or some potential level of treatment. Then I'm going to require this pi TE to be written as in this equation with some negative weight alpha on the predicted effect level. So the idea behind this negative weight alpha is that each treatment should be cheaper for experimental subjects who are more likely to be benefiting from this specific treatment T. Okay, some effectiveness-based price personalization or price discrimination going on. Then, given these personalized prices, each subject is going to solve a constraint utility maximization problem. Specifically, this P star IT, okay, is the probability that subject I is assigned to treatment T. Then for each subject I, I'm going to require the combination of the vector of treatment assignment probabilities to the solution to the utility maximization problem, okay, in the middle on the right-hand side. So in this utility maximization problem, okay, each person is trying to maximize the expected willingness to pay for assigned treatment, okay, but subjected to some budget constraint. And the budget constraint is formed by the personalized prices coming from the first step, as well as a common budget B, the blue object. And this blue object, the common budget, is picked by the experimenter at some sort of constant number, okay, which is the same for every subject. Then finally, I also require some innocuous capacity constraints. Okay. Then let's find any treatment assignment probabilities P star that satisfy all of these equilibrium conditions. Then for those who are sort of familiar to mechanism design, this is clearly a version or an extension of the very classic idea in economics and mechanism design, that is competitive market equilibrium from equal incomes, which has a very long history, at least since 1960s. And from the purely sort of economic or mechanism design perspective, this is the end of the story. But from the experimental design perspective, there remains some problem. That is, this assignment probability P star may be equal to 0 or 1, so that there will be no randomization anymore. So to deal with this problem, I'm going to add just one more modification to the previous definition. That is, starting from the P star thing on the last slide, let's modify it to what I denote by P star of epsilon. Okay, this orange object. This P star of epsilon, okay, it's just a mixture of the original P star, okay, and the RCT assignment probability, such that the resulting mix is always bounded between epsilon and 1 minus epsilon for every subject I and for every treatment T. And here, this epsilon is some design parameter, okay, picked by the experimenter as some small constant, such as 5%, maybe 10%. Okay, so given the experimenter's choice of this epsilon parameter, okay, let's compute this P star of epsilon object, which will be the final treatment assignment probability, okay, in this exam, okay, or experimental's mark. But if you are confused by this slightly messy definition, then you can take this P star of epsilon or exam as some black box algorithm that will compute assignment probabilities based on your data. But at the very least, I should convince you that this exam is not just a sort of crazy monster that comes from nowhere, but rather a natural extension of the usual RCT to think about. So to clarify this point, let's imagine a situation where the experimenter has no clue about willingness to pay or predicted effect. The very sort of classic scenario, okay, with no information, no additional sort of information about welfare. Then even in this scenario, it's still possible for the experimenter to implement the exam, right? Because the experimenter can simply sort of make both willingness to pay W and predicted effects E be the same and constant for everybody and every treatment. Then in this scenario with no welfare data, exam turns out to reduce to the usual RCT. In the sense that the two experimental design produce all the same assignment probability for everybody and every treatment. So therefore, this exam is a strict enrichment of RCT, okay, developed to incorporate the additional information about willingness to pay and the predicted effect. Then in general, of course, there are millions of possible ways to incorporate the data about willingness to pay and the predicted effects. Then, so why should we use this particular design of exam? So my preferred answer is that this exam has a particular welfare optimality property in the spirit of the first fundamental theorem of welfare economics. What I mean by that is that exam, okay, are optimally randomly assigned each treatment to subjects with better predicted effects of that treatment, or to subjects with higher willingness to pay for that treatment. More precisely, for any feasible choice of the epsilon parameter, there always exists a combination of assignment probabilities that satisfies all of the exam conditions. So some equilibrium existence result. Then for any such assignment probabilities in exam, it is ex ante Pareto optimal in the following sense. That is, there is no alternative experimental design P without a star, okay, with the same random assignment condition such that the alternative design, Pareto dominates exam in terms of these two welfare measures listed here. The expected willingness to pay for assigned treatment and the expected predicted effect of assigned treatment. So therefore, as long as the experimenter cares about these two things, the expected willingness to pay and the expected predicted effect, there is no alternative experimental design that is clearly better than exam from the ex ante perspective. So in this sense, exam has the good welfare optimality property. Then in this result, I take this willingness to pay data W as given and as representing the true preferences of experimental subjects, right? But in practice, these preferences and willingness to pay are, of course, private information, okay, held by experimental subjects themselves. So therefore, in practice, the experimenter needs to ask experimental subjects to report their preferences about different types of treatments, right? And in this sort of preference reporting or willingness to pay reporting process, one concern is incentive compatibility. That is, whether subjects find it sort of optimal and makes sense to simply report the true willingness to pay to the experimenter. And the theoretical answer to this question turns out to be yes, in the sense that exam can be shown to be incentive compatible for willingness to pay reporting, at least for large enough experimental design problems. So it is almost always optimal for experimental subjects to report the true willingness to pay to the experimenter when experimental subjects are trying to maximize, okay, the private benefit coming from that willingness to pay reporting. So in this sense, exam is welfare optimal in an incentive compatible way. Then the final methodological question is probably what about information, right? That is, since this is an experimental design, we'd like to use the resulting data coming from this exam experimental design, okay, to estimate treatment effects and policy effects. Then to provide an answer to this question, Suppose that the experimenter cares about the causal effect of each treatment on some outcome yi, which is the observed outcome for each subject I. Okay? Then I use this usual yi of t symbol to denote subject i's potential outcome when subject I is hypothetically assigned to a particular treatment t. Okay? Then, of course, many of these potential outcomes are simply unobserved, so that the experimenter wants to estimate or learn a certain parameter of this unknown distribution of potential outcomes. And let's denote that parameter of interest by theta. Okay, one possible example of theta is the average treatment effect for this population of experimental subjects. Then finally, I'm going to use this WBIT to denote the indicator that subject I is assigned to treatment T. Okay? Then with these pieces of notation at hand, I'm going to say that this parameter theta is unbiasedly estimable with any given experimental design P, okay, if the following is true. That is, there is some estimator theta hat, okay, which is a function only of observed outcomes and observed treatment assignments, such that this estimator is unbiased for this parameter theta when the data generating process is given by this experimental design P. And it turns out that whenever some parameter theta, okay, is unbiasedly estimable with RCT, this same parameter is also unbiasedly estimable with exam with any positive choice of the epsilon parameter, at least for a wide class of parameters containing the average treatment effect and other important effects. So therefore, first observation is that exam is no worse than RCT in terms of the set of parameters unbiasedly estimable with each experimental design. Then one consequence of this result is that exam allows the experimenter to unbiasedly estimate the average treatment effect, right? Because the average treatment effect is known to be unbiasedly estimable with the usual RCT. Then why is it the case that exam can unbiasedly estimate the average treatment effect? The simplest possible answer is that at the end of the day, exam is just a particular stratified experiment, stratified on observable characteristics, especially the willingness to pay W and the predicted effects E. So in exam, okay, treatment assignment is not based on a coin toss, okay, but rather based on, okay, some utility maximization problem, right? But imagine that, say, I and Max share the same values of willingness to pay W and the predicted effects E. Then the two of us will face the same constraint utility maximization in exam, so that the two of us will get the same vector of treatment assignment probabilities at the end of the day, right? So therefore, as long as some sort of two persons or two subjects share the same value of W and E, the resulting treatment assignment is going to be conditionally randomly assigned and conditionally independent from anything else. So therefore, by the classic propensity score logic, the same conditional independence holds, okay, conditional on the vector of treatment assignment probabilities or propensity score as well. Then this observation motivates, okay, a variety of possible estimators of the average treatment effect using exam data. So one possible way to go is just this one. That is, as a first step, let's focus on a subsample of experimental subjects, okay, who share the same value of the treatment assignment probabilities. Then let's regress the observed outcome yi on observed treatment assignments dit to get these coefficients beta pt's. And this beta pt is an unbiased estimator of the conditional average treatment effect of each treatment t on the final outcome for this subpopulation of individuals with a specific value of the treatment assignment probability. Then to move from these conditional average treatment effects to the unconditional and global average treatment effect, it only remains to take a particular weighted average of these coefficients. So for example, if we weight these beta PTs based on the population fraction of each subsample relative to the total number of experimental subjects n, then the resulting weighted average of beta PTs turns out to be an unbiased estimator for the average treatment effect. So by using this estimator or other similar estimators, it's possible to estimate the average treatment effect and other key treatment effects using exams data. Then this is a point about bias. And in the paper, I also provide some discussions about variance as well. And one observation is that even in terms of variance, it is not necessarily the case that exam is worse than RCT. And in fact, so there are certain situations where exam's average treatment effect estimator is more precise than RCT's usual average treatment effect estimator. But in general, the variance comparison between exam and RCT remains ambiguous and remains to be an empirical question. So in the last few, then in the empirical application, I use data from a water source protection experiment done in Kenya a little while ago. And this experiment, fits into my framework as follows. That is, experimental subjects are about 1,500 households in the original experimental sample who are randomly assigned to a binary treatment of the protection of the spring in use at the baseline versus no such protection. So here the protection means that means some cleaning up of unprotected springs on the left, into something like the right one. So the experimental NGO tried to improve the quality of these springs or water sources, to avoid a bunch of bad outcomes such as child diarrhea. So as a primary outcome, I'm going to use the incidence of child diarrhea and the heterogeneous treatment effect of this treatment T1 on this diarrhea outcome corresponds to that E symbol in my model. Then on top of that, an additional piece of data about household water source choices also allows me to estimate households' heterogeneous willingness to pay for this spring protection treatment. So I'm going to use this data to estimate both E and W, then use the estimates to implement exam and compare exam with RCT in terms of important properties. And here is a summary of my findings. So in terms of subject welfare, exam turns out to be substantially better than the RCT. For example, this is the distribution of the welfare measure, the willingness to pay welfare measure on the x-axis, while the y-axis is its cumulative density. And then this dotted blue line is the distribution of welfare and the RCT. Now, what happens if we switch from this to exam? The resulting new distribution is this red solid line. There is some first order stochastic dominance improvement, and the average value indicated by the vertical line improves by about 90%. So exam seems as much welfare better than RCT. Then despite this welfare merit, exam's average treatment effect estimation turns out to be also as unbiased and as precise as RCT's average treatment effect estimation in this particular setting. So here, this blue distribution is the distribution of average treatment effect estimates under RCT. If we switch to exam, the resulting distribution of average treatment effect estimates is this red distribution, which is very similar to the original blue one, right? And the similarity between these two distributions, blue and red, shows the following 2 points. So first of all, both exam and RCT, have very little bias, and both of them allow almost unbiased estimation of the true treatment effect. On top of that, the two designs share very similar standard deviation or standard errors or variance in this average treatment effect estimation. So therefore, if we summarize what I talked about, this experimental market or exam is a solution to the following hybrid problem of mechanism design and experimental design. That is, we'd like to maximize the welfare of experimental subjects, but subject to the constraint that we need to provide as much information and as much incentives for truth telling as in RCT. Then the empirical results from this data about the Kenyan water source protection experiment is consistent with the theoretical results. So we can achieve some welfare improvement at almost no cost in terms of information and incentive. So I'd like to interpret this exam as a potential modification or enrichment of RCT when the experimenter cares a lot about subject welfare. So the final point is that sort of the general takeaway is that sort of economic thinking could potentially contribute to facilitating the advancement and use of complex, adaptive, and other novel clinical trial designs, which is one of the performance goals set by the Food and Drug Administration for 2018 to 2022. And today's discussants have even sort of more clear contributions to this goal. So I'd like to engage in additional discussions about this general point in the Q&A section as well as the breakout room. Thank you so much.
So you just sounded sort of super exciting, and this terminology of this disruptive monetary policy also sounds exciting. But I think sort of this is kind of a fake, and I personally think sort of there's nothing really sort of super new or exciting in this disruptive monetary policy, I think. That is sort of by the disruptive monetary policy, we sort of tend to mean sort of things like aggressively buying corporate assets and private assets, including illiquid ones like corporate bonds. But sort of these policy responses are not sort of really monetary policy in the traditional sense, and they are almost like just a version of fiscal policy. So in my sort of understanding, this disruptive monetary policy is just a politically easier version of fiscal policy responses to today's economic problems. Then why do we do that? The reason is simply because the monetary policy in the narrow sense is now almost completely ineffective. There's a strict lower bound on the nominal interest rate, so that there's not much room for monetary policy to play around with the economy. So in that sense, the disruptive monetary policy is not a disruption or innovation at all. And I think what we really need is a real disruption or innovation in monetary policy. For example, sort of allowing for real negative interest rates by digitalizing the fiat money, for example. So that's kind of my take about now. So one distortion I see is the impact of this monetary policy situation on inequality, I think. And so following up on what sort of Aya said, sort of the stock market is saturated sort of across the globe. So for example, sort of American universities like Harvard and Yale are running so huge hedge funds like tens of billions of dollars. But for them, sort of the stock market is no longer very attractive. So in the portfolio of Harvard a year, now the US stock market is something like just 5% or something. And a much bigger category is a very sort of unconventional things like mountains and forests and so on. So the stock market is almost completely saturated. And the consequence of this saturated stock market is that certain industries and certain companies disproportionately benefit from this situation, which is partly created by monetary policy, I think. And a lot, sort of much of the inequality problem in the past 20 years in the US and some other countries is coming from this distortion in the stock market. And I think sort of not much has been done to sort of deal with these problems directly. So this sort of inequality effect of the stock market bubble is one big distortion I see in today's situation. So we are halfway through the discussion, so probably we should sort of start talking not only about the past and the present, but also the future, I think. And following up on sort of Jennifer's proposition that monetary policy will disappear, I think monetary policy will be obsolete if there will be no real sort of technological advance or real disruption in monetary policy. And among other things, sort of one big technological constraint in monetary policy today is the hard lower bound constraint on the nominal interest rate. That is, the nominal interest rate is bounded by around zero, okay, due to some weird sort of historical reason. And why is there this constraint? The reason is mainly because the fiat money is issued in paper, in a physical form. And it's very hard to break this constraint with this paper fiat money. But we can break this constraint if we completely digitalize money and cash. And the Bank of Japan and many other central banks started talking about this possibility of trying to go to completely sort of digital monetary world. And I think this is one of the potential real disruptions in monetary policy. And once this sort of constraint will be obsolete, then monetary policy will no longer be obsolete.
So talk to me, what does that actually mean?
It means that you can set any interest rate between plus infinity and minus infinity. And it opens the sort of the door to a whole new possibility or set of options the central bank can take. So in the short run, sort of investors and direct sort of stockholders and employees and entrepreneurs around these industries in the short run, right? But in the medium to long run, sort of what I'm interested in is the sort of the trickle down effect on sort of players who are not originally in this game. That is, this sort of excess cash supply by the central government now sort of seduces lots of players outside of this specific industry. So for example, even in Japan, the University of Tokyo is now trying to issue sort of university bonds. And many of these sort of unconventional players are trying to enter this market to get sort of to benefit from this. So in the long run, I'm not very sure about the total effects and how the sort of this sort of entire benefit will be divided across different sectors. So, but I think the problem is very complicated now. No, in the age of the digital currencies, the power of central banks will likely to be bigger than today, simply because the spectrum of options for the bank will be larger. Then how to control them? I don't have a great answer as of now, and how to sort of control them sort of while maintaining the independence of the central bank. So that's something sort of we should discuss sort of in parallel to the design of sort of digital currencies, I think. So I don't have a very sort of specific proposal about that.
Thank you so much for having me. So today I'm going to talk about algorithm as experiment. So this is an econometric method project inspired by a variety of applied domains, including market design as a key application. So this is a joint work with Kohei Yata, who is a PhD student of mine, and he will be joining Wisconsin-Madison from this fall. Then the motivation for this project is very simple and very broad. That is needless to explain to this cloud, but now it's sort of the golden age of decision-making algorithms, right? That is computational algorithms in market design and many other fields such as machine learning are now producing more and more treatment decisions and recommendations in the real world. And here are just a few of the most fashionable applications of such decision-making or resource allocation algorithms. The point of this project is to take a specific econometric look at the surge of algorithmic decision-making. That is, I'm going to claim that these algorithmic treatment decisions and recommendations produce very high-quality natural experiments or instrumental variables that are useful for doing causal inference and improving the performance of these algorithms. That is, the central claim of this project is that algorithm is a natural experiment in a very broad sense. Then why is it the case that algorithm is a natural experiment? So let me start with very abstract and general intuition first. So assume that some algorithm is now running to make some decision or recommendation, which I denote by Z. Okay. Then this algorithm makes this decision Z based on a bunch of input variables collected into a vector X. Then by definition or by construction, nothing else will directly influence the decision output Z other than these input variables in X, right? Because by construction or by definition, any algorithm is designed to use only a pre-specified set of input variables. Importantly, these other irrelevant variables include not just observable variables, but also any unobservable variables as well. Therefore, once we condition on X, that is, once we focus on situations or individuals with the same or similar values of X, then the decision output made by this algorithm is going to be statistically independent from anything else. In other words, this decision output Z is going to satisfy the conditional independence assumption the econometrician always wants to assume. So therefore, this decision output Z is going to work as a good instrumental variable for whatever final treatment we are interested in. The goal of this project, or the theoretical goal of this project, is to formalize and operationalize this intuition as a widely applicable treatment effect estimator. So our theoretical analysis is going to start with an identification analysis. Here, we are going to characterize exactly what causal effects we can identify when we have data generated by any given data generating algorithm. And we are going to provide an answer to this identification question for a broad class of algorithms containing both stochastic and deterministic algorithms. This identification analysis then clarifies that the data from almost every algorithm allows us to identify at least some causal effect. Then, in the main theoretical part, we are going to translate this identification insight into a specific estimator of a treatment effect. And we are going to formally prove that our treatment effect estimator is consistent and asymptotically normal for a well-defined causal effect, even in the presence of lots of heterogeneities in treatment effects. And our estimator is also easy to compute and straightforward to implement, even if the input vector X is high dimensional and the decision-making output is complex. So in general, the decision-making algorithm may contain some crazy components like deep learning or very complicated machine learning components. Even in that case, okay, the final treatment effect estimator can be made very simple. Okay, and the same point can be said, okay, even if the decision-making algorithm is a complex market design one, such as the deferred acceptance algorithm or the top trading cycles algorithm. A key special case of our estimator or our econometric method is a high-dimensional regression discontinuity design. That is, in the previous conceptual framework, okay, imagine that this input X, okay, contains a bunch of learning variables that jointly determine whether each person gets treated or not. Then this framework effectively nests a multi-dimensional extension of the regression discontinuity design with any number of learning variables contained in X. Right? So therefore, our proposed estimator can be interpreted as a consistent and asymptotically normal estimator that can be applied to the high-dimensional RDD or regression discontinuity design with an arbitrary number of learning variables. Okay? Then after developing such a treatment effect estimator, I'm going to also talk about a bunch of applications and examples. And our framework is a fairly abstract one, so that it has many potential applications. So the first group of important applications is decision-making made by machine learning algorithms. And there are a variety of different types of machine learning algorithms, starting from naive, simple supervised machine learning to more sophisticated bandit and reinforcement learning type dynamic optimization algorithms. So no matter which specific algorithm is being used for making the decision making, okay, the resulting data generated by such machine learning algorithms, okay, can be analyzed by using our method. Then on top of machine learning applications, there are many social and economic applications as well. The second group of applications, okay, is related to market design and centralized mechanism design. So I'm going to talk more about this point, but think about auction algorithms or matching and assignment algorithms. At a very high level, these market design algorithms are just particular examples of decision-making algorithms that use some observable information to make some decision or resource allocation, right? So in that sense, the data coming from market design can also be analyzed by using our data. And I'm going to talk about a particular application using data coming from the school choice matching mechanism, okay, as a first sort of application coming from a prior joint study of mine. Then the final group of applications is related to public policy eligibility rules. So think about, say, a particular policy domain like Medicaid in the US, okay, or many other similar policy domains with resource constraints. So in such policy domains, okay, the government often uses some algorithmic rule, okay, and observable characteristics of individuals or households to determine who are eligible for that policy, right? That is, whether a particular individual in the US is eligible for Medicaid or not is determined by a particular sort of rule or formula or algorithm, okay, applied to observable characteristics such as the income level and the family composition and so on, okay? Then these policy eligibility rules can also be taught as decision-making algorithms. So therefore, the data coming from such policy eligibility rules are additional examples of our framework. And as a particular original applications in that spirit, I'm going to use our method to evaluate the effect of hospital relief funding distributed by the US government during the COVID-19 pandemic. And this policy distributed hundreds of billions of dollars, okay, to struggling hospitals to help their efforts to deal with COVID-19 patients. And the US government used some a particular algorithmic funding eligibility rule so that the resulting data can be analyzed by our method. And we are going to use our method to find that this hospital relief funding probably had very limited or effectively no impacts on any hospital activities related to COVID-19, such as the number of COVID-19 patients accommodated by hospitals or the COVID-19 related mortality rate and so on. So our empirical bottom line is that probably this hospital relief funding made by the US government was close to a waste of money from the perspective of this particular policy. So I'm going to talk about both some theoretical development as well as empirical applications. But is there any comments or questions at this point? Great. So then let me jump into our framework. So our framework is a fairly simple econometric framework for estimating the causal effect of a particular treatment on outcome. So imagine that there are a bunch of individuals indexed by I, okay? So each individual I, okay, has a vector of fixed covariates denoted by xi, okay, which has p components. The support of this covariate vector, okay, is going to be denoted by this calligraphy x, okay? Then each individual I with these covariates xi is going to first receive some treatment recommendation, which I denote by zi, okay? For simplicity, this treatment recommendation zi is assumed to be binary, okay? Then the most crucial assumption made here is that this binary treatment recommendation is assumed to be made by some known algorithm, which I denote by this A, okay? Then this A is just an algorithm or function, okay, that maps each possible covariate value in this covariate space, okay, into the unit interval, okay? The interpretation here is that the output of this algorithm or the function A is the conditional probability of a treatment recommendation when individual I has a particular covariate vector value, okay? Then the important point is that this algorithm A, okay, may be either stochastic or deterministic. That is, the output of this function A may be either 0 or 1, so that this can be a deterministic function, okay? So this binary treatment recommendation Zi is assumed to be made by a known algorithm that may be either stochastic or deterministic. Then after that, each individual is going to receive a final treatment assignment, which I denote by Di, okay? Then if I use this Di of Z to denote the potential or hypothetical value of this treatment assignment, when individual I's treatment recommendation is fixed to a particular value, small z, okay, I can write this final treatment assignment in this way, which is familiar to those who know a lot about econometrics. Okay, then finally, each person is going to generate some outcome, which I denote by yi. Okay, and again, if I use this yi of d to denote the potential outcome, when individualized treatment assignment is being fixed to a particular value, small d, then this observed outcome can be written in this way. That is, when individual I gets treated, okay, we are going to observe this y of 1. And when the individual I isn't treated, then the observed outcome is going to be this potential outcome, okay, without any treatment. Okay, then for those who are familiar with this kind of causal inference framework, this is a very standard framework of causal inference with instrumental variable and observable covariates. The only departure from the standard setting is this highlighted part. That is this treatment recommendation Z, okay, or the instrumental variable Z, okay, is being assumed to be made by a known algorithm. And this twist makes this setup interesting and tractable, as I'm going to show in the next 10 minutes. Okay, any questions about this model and the framework? That X is independent from DI. So X is assumed to be fixed and given. So in that sense, this X is a deterministic object so that it's independent from anything else. Another related point is that this Xi changes the distribution of this binary treatment recommendation Zi. And this Zi treatment recommendation may be systematically related to this treatment assignment. So in that sense, there is some sort of connection or link between Xi and Bi.
Thank you.
Yes, great. Any other questions about the framework? Great. So then to make some progress, I need just a few regularity conditions or assumptions. The most crucial assumption or property, okay, is the following conditional independence property. That is, this algorithm A makes its treatment recommendation Zi only based on these observable characteristics or input variables Xi. So therefore, conditional on Xi, that is, among individuals with the same values of Xi, okay, whether each person gets treatment recommendation or not, is independent from anything else. In particular, potential outcomes Y1 and Y0, and the potential treatment assignments D1 and D0. Okay, then I'm going to assume this conditional independence property throughout, and note that this conditional independence property, okay, is not really an assumption, but rather a true property or fact guaranteed by the construction of the algorithm in many applications. Then I also need to assume a few, okay, regularity conditions. The only substantive regularity condition is this first one. That is, this algorithm A, function A, must be continuous almost everywhere. So this may involve finitely many discontinuous points, but almost everywhere it must be continuous. Okay. Then only for this presentation, just for simplicity, we assume that this Xi vector contains only continuous components, and the paper extends the entire analysis to the case, okay, with discrete components Nx. But this continuous X makes the notation and the representation much simpler. Okay, so then to connect this framework, okay, to sort of something which you already know, let me sort of explain a few important special cases or examples of this framework, just to make sure that everybody is on the same page. So one of the simplest special cases of this framework, okay, is probably a stratified RCT or selection on observable or the propensity score scenario. That is, imagine that this algorithm A, okay, or the treatment recommendation probability made by this algorithm, it's strictly between 0 and 1 for every possible value of X. Then this effectively means that everybody is facing some explicit randomization or stochastic treatment recommendation, okay, in a way that uses only the information about X. Then this is effectively a stratified experiment, okay, where treatment assignment probabilities may be different across different individuals with different covariate values. So this is a very simple setup or special case, and we know what to do in this special case. But this framework also contains many other interesting scenarios. For example, another example is the regression discontinuity design. So imagine or assume that, okay, this input vector X contains only a scalar running variable. Okay, then conditional on any value of this scalar running variable, okay, the treatment recommendation probability is either 0 or 1, so that it's degenerate. Okay, but as we move across different values of the running variable, okay, this treatment recommendation probability jumps from 0 to 1 or 1 to 0. Then this is a familiar regression discontinuity design, okay, where the treatment assignment is sort of deterministic, but depends only on this scalar running variable. So in this sense, our framework is an integration of the first stratified RCT example and the regression discontinuity design. And because of this integration, this framework contains many other complicated scenarios, such as machine learning algorithms and market design algorithms under high-dimensional RDT. Okay? And there's no established or standard estimator, okay, for this most general setup with imperfect compliance, okay, and the no overlap condition or the violations of the full support condition. So our methodological goal is to provide a widely sort of easy to use estimator that can be applied to any example in our most general framework. Okay. Then before sort of showing our estimator proposal, let me also explain how sort of this framework is related to market design. So here is sort of how matching and auction, okay, can be nested into our framework. So let's first think about the case of matching or assignment. So in this case, okay, in the school choice analogy, individuals I correspond to, say, students or families participating into the school choice matching algorithm. Okay, then sort of each student has a bunch of pieces of observable information, such as the preference of order over schools and the priority status at each school, and maybe some tiebreaker like test scores or lottery numbers, right? The vector of all of these input informations used by the mechanism is X, okay? Then some known algorithm or mechanism, maybe deferred acceptance, maybe top trading cycles, or maybe immediate acceptance algorithm, determines whether each student I is assigned to a particular school or the treatment school. Then this assignment variable corresponds to our Z. Then we may be interested in, okay, the effect of attending the treatment school DI on students' future test scores. So this is a particular way, okay, a matching algorithm can fit into our framework. Then auction is also a possible example of our framework. There are a bunch of bidders that correspond to individual I in our framework. Okay, then each bidder has an observable bit contained in the data, maybe along with some additional characteristics that matter for the final allocation. Then the given auction algorithm determines, okay, which bidder wins the good at which price. So that sort of auction outcome is our Z variable. Okay, then we may be interested in the effect of this auction outcome on bidders' future economic performance. So in this sense, market design algorithms can also be taught as examples of our framework. That environment with perfect compliance is a particularly easy example of our framework. But our method can be used even if this Z and D are completely different from each other. So in many school choice applications, many students students' enrollment outcomes often deviate from their assignment outcomes. So in that case, this Z and D is going to be different from each other. So our method can be used in that setup as well. But if there is perfect compliance, it will be easier. Okay, so then our goal is to provide a method to estimate the effect of D on Y. Okay, and here is the proposal in a single slide. So if you are an empirical researcher, so this slide is the only thing you should remember at the end of this presentation. Okay, then our goal or our question is the following one. That is, suppose that we have a sort of finite sample or data set generated by the previous framework with some known algorithm A. Then how should we use this data to estimate the effect of the treatment assignment D on the final outcome Y? Here is our proposal. Our proposal is the following two-step estimator. The first step, okay, is an intermediate simulation step. Let's pick some small bandwidth value delta, okay, as well as a large integer s as the number of simulations. Okay, so these are some design parameters picked by the analyst and the econometrician. Then, given these two values, okay, we are going to first simulate these objects x star 1 to x star s. And these are, okay, a bunch of independent draws from the uniform distribution over the p-dimensional delta ball around individual i's covariate. That is, in the covariate space, each individual eye has a particular covariate point, right? Then let's think about a small ball or neighborhood around that covariate point. Okay? Then we consider the uniform distribution over that ball, which I denote by this capital B. Okay? Then let's draw a bunch of sort of independent covariate values from that uniform distribution over the neighborhood. That's what these X star objects try to denote. Okay? Then let's substitute each simulated covariate value, okay, into this algorithm A. Then this is going to produce some associated treatment recommendation probability, right? And let's compute that treatment recommendation probability, okay, and take the empirical average over many simulations, capital S simulation. Okay, the final average is going to what I'm going to denote by this blue object, P of X delta. Okay, then this object is effectively a sort of simulation approximation to the approximate value of the treatment recommendation probability, okay, in a small neighborhood around individual eyes covariate value, right? And I'm going to call this object the approximate propensity score in the paper, or APS in short. Okay, then this treatment effect estimator, okay, then combines this first step simulation object or the approximate propensity score, okay, with the familiar two-stage least square instrumental variable regression. That is, after the end of the day, we are interested in how this outcome yi, okay, is impacted by this treatment assignment di, right? But of course, this treatment assignment is far from randomly assigned, okay, so that we need to find some instrumental variable for treatment assignment. Our proposed instrument is this zi, which is the outcome of our algorithm A. Okay, then to make this algorithm out of zi a good instrumental variable, we need to control for some appropriate object to make this z, okay, conditionally randomly assigned. Our proposed control, okay, is this one. That is, we propose to linearly control for the approximate propensity score coming from the first step simulation. Okay, then our final estimator, okay, is this beta object. That is, this is the two-stage least square estimator coming from this specification, linearly controlling for the propensity score. So our main theoretical result, okay, is that this beta estimator coming from this two-step procedure is consistent and asymptotically normal for a well-defined causal effect, even in the presence of treatment effect heterogeneities. So in this sense, okay, this algorithm A may take a variety of different forms. This may be deferred acceptance. This may be some combinatorial auctions. This may be some crazy machine learning algorithm. But what we should do at the end of the day, okay, is to blindly apply this two-step procedure, okay, without worrying too much about the details of the definition of the decision-making algorithm. So no matter which specific algorithm is being used, this beta estimator is kind of good enough. Any questions about this definition of our treatment effect estimator? But unlike the Heckman selection model, here sort of this P term, this part, it is in a sense a known thing. That is, we know this blue part from the first step simulation, right? And we don't need to estimate this blue part so that we don't need to worry about the kind of the independence or the lack of dependence between this Z part and this P part. So since we know this P function from the first step simulation, even if this Z variable is a linear function of Xi, I think this two-stage least square regression is going to go through. That doesn't matter because this P is some known function. We don't need to estimate it, so that we don't need to care about sort of the identification or the estimation of this P part. That's the key, I think. So in this sense, this framework is really sort of using the assumption that we know the algorithm and we know this approximate propensity score P from the first step simulation.
Thank you.
Yes.
So I'm wondering if you could.
Yeah, so the typical sort of candidate for Y in an auction example is some sort of future economic performance or future business KPI or beta I, right? So in a sort of existing empirical paper, some marketing folks sort of looked at data coming from online advertisement auctions done by Google and Yahoo and so on. And they analyzed sort of whether winning an advertisement auction really sort of improved their advertisement sort of revenue bottom lines, say weeks after the auction. So that's the typical choice of this outcome Y. So such additional steps or administrative adjustments are going to generate some discrepancy between Z and D, that is a treatment recommendation versus the treatment assignment. And the discrepancy between Z and D is going to make the final estimator less statistically efficient and less precise than we would hope. But the entire framework, so the basic framework of our method, it's going to be valid sort of no matter how many additional steps are there and how many additional compromises there are to the connection between Z and D. Okay. But if this Z has really no influence on the final sort of treatment assignment D, then the data coming from the matching mechanism is going to be effectively useless. Right. So we need to have some continuous covariates. And in the case of matching or school choice application, such continuous covariates are typically test scores or lottery numbers or something like that. So we need to have some continuous covariates. That's right.
Okay.
So it may help to explain a particular market design application then. So one possible application of our method is that to data coming from school choice matching mechanism. And in a prior sort of application, we are looking at whether sort of attending selective elite schools are really beneficial for students or not. And we did this analysis sort of motivated by some policy discussion about the inequality in access to elite schools in New York City. So this is a sort of old or prior application I did with Attila and Josh and Parag in our now published papers. And in this empirical application, we estimate that the effects of attending elite schools compared to ordinary schools by using data coming from New York City's deferred acceptance algorithm. And this setup corresponds to our framework in this way, which is very similar to what I explained before. And your question is related to this algorithm input, I think. And this xi, of course, contains student i's preference order over schools, as well as each student's priority status at each school. Okay? But on top of this, New York City uses both test score tiebreakers as well as lottery number tiebreakers. So this xi contains all of these things, and test scores and lottery numbers are continuous input variables that produces real quasi-experimental variation. Okay, and here, so we are interested in a particular group of elite schools called grade A schools in New York City, which contains many of the most selective schools in New York City's sort of main high school choice system. Then we are interested in whether attending any one of these grade A elite schools, this one, affects each student's future test scores and other outcomes. Then to do that, we are going to use the assignment made by the deferred acceptance algorithm as our Z, which creates some quasi-experimental variation in the final treatment. Okay. Then the bottom line of this empirical application is that these elite schools appear to have little to no causal effects on students' future outcomes. To do that, we looked at three important outcomes. So SAT math test score around the graduation points from these high schools, SAT reading test score, and finally, high school graduation outcome. Okay, then for each one of these outcomes as our Y, okay, we use the slightly modified version of the previous estimator to estimate the effect of attending a grade A school on that outcome. Then the starting benchmark is this blue bar. So for each outcome, this big blue bar is the simple comparison, or simple difference between grade A schools versus other schools. That is, so without controlling for anything else and without using our method. Okay, so then this means that this suggests that these blue bars say that grade A schools are, of course, okay, are much better than other schools in terms of any one of these outcomes. Okay, students at grade A schools tend to have much higher SAT scores, and the students at grade A schools are more likely to graduate from high schools. So no surprise, and this is just a sanity check. Then the final bottom line is this gray bar. Okay, so this gray bar is our two-stage least square estimates, okay, using the instrumental variable or the quasi-experimental variation generated by lottery numbers, okay, as well as test score tiebreakers. And once we incorporate this natural experiment in a precise way, okay, then these gray bars look much shorter than blue bars and very close to zero. And this means that probably the original apparent difference between grade A schools versus other schools, okay, shown in blue bars, is driven mostly by selection bias instead of a true causal effect. Okay, and these gray bars show that the real causal effect of attending grade A schools on these outcomes is probably very close to zero, at least according to the specific quasi-experimental variation we can exploit. Okay, so then this is one way we can use our method to estimate, okay, the effect of school attendance by using market design data. Then the next final application is an original new application that also clarifies the power of our method in a completely separate domain. So this empirical application is about the so-called CARES Act, which is an abbreviation for the Coronavirus Aid, Relief, and Economic Security Act. And this is probably one of the biggest economic stimulus package in the entire US history. And this act distributed hundreds of billions of dollars in relief funding to hospitals to deal with COVID-19 patients. And the policy goal was to simply sort of help financially insecure hospitals because they may be less capable of investing in COVID-19 response efforts. Then the goal or the research question in this empirical application, okay, is whether this problem was really alleviated by this hospital funding or not. That is, what was the real effect of hospital funding on COVID-19 related hospital outcomes. To do that, we are going to use the following institutional sort of feature. That is, in this policy, okay, whether each hospital is eligible for getting this funding or not was determined by an algorithmic rule applied to 3 hospital characteristics. So this is not a health economics seminar, so you don't need to understand the exact definition of each characteristic, but effectively these 3 conditions, okay, about 3 particular hospital characteristics, okay, are pinned down whether each acute care hospital was eligible for this policy or not. And the intention behind this rule was to simply target hospitals, okay, that provide care to the most vulnerable part of the population and operate on thin margins. Then a visual version of this funding eligibility rule is shown here. So let's take a look at this 3D space. Okay, this 3D space is spanned by the 3 hospital characteristics that jointly determine funding eligibility, okay, such as the profit margin. Okay, then dots or marks in this 3D space are hospitals in our data. Okay, then red circles correspond to eligible hospitals, while blue marks correspond to ineligible hospitals. Okay, then from this 3D picture alone, it's hard to see what's really going on. So let's extract a couple of 2D planes from this original space. Something like this. So each plane, okay, focuses on 2 out of the 3 hospital characteristics determining funding eligibility. Then as you can see in each 2D plane, okay, there is some sort of discontinuity, okay, in the determinants of funding eligibility, right? That is, in this plane, okay, this boundary, okay, dramatically changes whether hospitals are eligible or not. And in this plane, okay, a similar boundary is here. So this means that the original 3D space is a collection of infinitely many, okay, such 2D regression discontinuity design or boundary discontinuity designs. And our framework provides an automated way to extract all of the instrumental variables or quasi-experimental variation embedded in this 3D space. Okay, so we used our method to estimate the effect of the amount of funding on the COVID-19 related outcome. So here, okay, the 3 eligibility determinants correspond to that vector of input variables xi in the theoretical framework. Then this x determines whether each hospital is funding eligible or not, which is our z. Then our treatment is this d, which is the amount of funding each hospital gets, okay? And we are going to estimate the effect of this funding amount on the number of COVID-19 related patients accommodated by hospital I, okay? Then here is the main empirical result. So naively speaking, okay, looks like this funding policy appears to have some positive and significant sort of effect on this COVID-19 outcome. For example, if we use simple OLS regression, okay, that simply compares eligible versus ineligible hospitals, or if we use naive 2-stage least square regression without that approximate propensity score control, okay, then we find, okay, a highly statistically significant and economically significant effect of funding on the number of COVID-19 patients. Okay, for each $1 million of funding, okay, the average hospital gets about sort of 3 to 5 more COVID-19 patients, okay, in the hospital. Okay, but once we control for the approximate propensity score, according to our theoretical framework, then all of these significant stars go away. And the estimate of the effect of funding on the number of COVID-19 patients becomes even negative. Then this suggests that probably the original significant sort of effect of funding on the number of COVID-19 patients is probably due to selection bias, mostly speaking. And the real causal effect of this funding is probably pretty close to zero. And the same results even for the number of patients in ICU, and the same results even several months after the distribution of this funding. So here, the horizontal axis is time, and the vertical axis is the estimated effect of funding on the number of COVID-19 patients at each point in time. Then across the board, the estimated effect from our method, blue line, is around 0.0 and is never significantly different from 0. So in this sense, our analysis provides some sort of causal support for the widespread media concern. Okay, a lot of people talked about sort of at the start of this policy. That is, a lot of people sort of thought that this funding algorithm was not very well targeted. Okay, and the hospital funding sort of was thought to go to hospitals that don't really need funding, or hospitals that are so financially poor that they cannot sort of use that funding to build up sort of enough equipment to deal with COVID-19 patients. So in this sense, sort of our analysis suggests that the media concern back then was a correct and precise one, and the funding algorithm used by the government should have been better designed. But I'm running out of time, so let me wrap up and summarize what I talked about. So the simple takeaway from this project is that now sort of algorithms in many domains are sort of taking over the world in several senses. And as sort of algorithm eats the world becomes a mountain of natural experiments and instruments. Then the question is how to analyze, okay, such algorithm-produced natural experiments for doing correct causal inference. And we provide a simple but general method that combines the simple two-stage least square instrumental variable regression with the so-called approximate propensity score concept. And we provide some theoretical justification or theorem as well as empirical applications. But that's it for now. So thank you so much for your time and questions, and I'd be happy to engage in any additional discussions. Yes, that will be probably feasible, hopefully feasible. So you are correct that in most machine learning applications, so the outside analyst doesn't really know exactly what algorithm was being used for creating that data. So in that setup, we would need to sort of estimate what algorithm was used. So we are sort of currently trying to expand this framework to the case where the algorithm is unknown and maybe sort of satisfied some shape restrictions and so on. And the analyst needs to sort of estimate that algorithm component A. And how to do that. So that's a little sort of tricky question from the theoretical perspective. So we are currently working on that sort of problem. So stay tuned, and then I'm hoping to sort of come back here to report our progress along that line.